Anshuman has asked a doubt over here. Okay, so first we're going to talk about the doubts. Suppose this is the equilibrium that you are having. Then Kp is equal to okay, and now partial pressure can be written as number of moles by volume. Rather than going this way, I'll use the expression that partial pressure is equal to mole fraction multiplied by P total. P total over here refers to P equilibrium only. I hope these steps are clear to you, beta. If there is any doubt, you may please ask me. Now this is delta Ng, gaseous moles of product minus reactants. Now mole fraction is nothing but number of moles over total number of moles. So Kp can further be written as okay, this is the expression that you've been asking about. Okay, is this clear, Anshuman? Okay. Okay, fine. Now let us come on to the basic topics. We'll have to we've already talked about the pH scale, right? We in this videos, if you would have seen, I've kept it pretty short. We have talked about the buffer solution, we have talked about the solubility product constant, and we have talked about the not the solubility product constant, the salt hydrolysis, right? So let me just give you a brief of all that, and then we will pick up certain questions on that. So we'll be talking about buffer solution, and then we'll be talking about salt hydrolysis, and then I'll be talking about the solubility product. Okay. We may start the organic portion today itself, once this gets over. Okay. So let's start with the buffer solution. Let me take a bigger board. Now, what do you mean by a buffer solution? There are two things which you need to remember. Whose pH does not change on dilution, and the second which tries to resist the change in pH on addition of small quantity of acids or bases. Okay, yeah. How many people have watched the videos of mine? Mithun, I have given many examples in the videos. Have you watched my video? Then I told you, human blood is a buffer solution. Didn't I told you? See, I'll explain you everything one by one. First, let's talk about this. Tell me, friends, if you have got a 10 raised to power minus 1 molar HCl, we mean that 0.1 mole of HCl is added to 1 liter water. Do you agree with this part? Do you agree with this part, beta? Tell me. Okay. Now, if, see, this is 1 liter water. Volume over here is 1 liter. If I add 9 liter water to it, the volume will become how much? 10 liters. And in that case, the molarity will become 0.01. And the pH will become 2. Here the pH was 1. If you add 99 liters, volume becomes 100 liters. pH becomes 3. If you add this much, volume becomes 1000 liters. So pH becomes 4. So as you can see, when we are diluting it to 10 times, the pH is increasing by 1. Further dilution to 10 times, pH increases by 1. Further dilution to 10 times, pH increases by 1. Right, but here we are saying that in buffer the pH does not change. So how come it does not change? Now see, the buffer solutions basically are of two types. First is acidic buffer. Now how do you get an acidic buffer? By mixing a weak acid plus strong base. You need to remember that the strong one is always in smaller quantity, or it should be the limiting reagent. For example, you add acetic acid mixed with NaOH, or you take HCN combined with KOH. Okay, or you take HF reacted with, say, NaOH, right? So weak acid, strong base. So these will result into the formation of buffer. There is one more way of looking at it. What is that way? Please pay attention over here. See, when these two combine, they will form this plus this. Now see, what is this? This acetic acid dissociate to give this one. Now since this is acid, this is, as per the Lorry-Bronsted theory, base. Which base? Conjugate base, right? So what can I call this? This can be called as salt of its conjugate base. Okay. So you can also get it by mixing a weak acid plus salt of its conjugate base. So if they ask you a question that if you mix or add these two, will you get a buffer? Yes. 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 So all these on mixing will give you the buffer solution. This is when you are mixing the two things, or they can ask you a question, which of the following is a buffer? So HCN and comma NaCN. Now, is this a buffer? Now, how we can identify whether this is a buffer or not? Now, this is a very, very crucial information, and it is a very nice trick. If you pay attention, you can solve this question within no time. See, first thing that you have to check is that this part is a weak one. So this is a weak acid. Okay, now see over here. You have to focus on this hydrogen. You have a hydrogen here, but you don't have a hydrogen over here. Because in the acid and the conjugate base, the difference is of one hydrogen. So if there is a difference in the hydrogen over here, it means that this is basically an acid and conjugate base pair. So this behaves as a buffer. Now to illustrate the same, suppose if you are given this question, H2CO3 Is this a weak acid? Yes. Now, if I write NaHCO3, can you call this mixture as a buffer? Yes, we can call. How come? See, you have got two hydrogens over here, whereas you have got only one hydrogen over here. So this is an acid-base conjugate pair. Okay, if you ask me, sir, what if I write H2CO3 and Na2CO3? Does this one act as a buffer? The answer is no. This one is right, this one is no. Why? Because here you see there are two hydrogens, but over here there are zero. This is not acid-base conjugate pair. Okay, fine. Similar way, NaHCO3, H2CO3. Can you call this as a buffer? Yes. Sorry, wait a second. This is a buffer. Why? Because here there is one hydrogen, but here there is no. So there is a difference of one hydrogen. Okay. So these are also termed as the buffer solutions. One which you obtain by mixing, second which contains. I write it over here. Understood? Okay. Now see, when you derive, we have already derived the expression for pH of a buffer. This comes out to be pKa plus log salt concentration by acid concentration. This is termed as Henderson's equation. Now, so what is salt? Salt is number of moles by volume, sorry, concentration. So here also it is number of moles by volume, here also number of moles by volume. The number of moles will differ, but volume of the solution remains same, so this gets cancelled out. So whether the volume is 10 liter or it is 100 liter or it is 1000 liter, it will get cancelled in the numerator and denominator. So pH will have no effect on the change in the volume. Okay, so tell me, is this part clear to everybody? Any doubts? Clear to everybody? Great. Now let us go ahead. Let me give you certain examples of a basic buffer also. Here you will say by mixing yes, can you tell me? You will get the basic buffer by mixing what? Hello? Yes. Okay. Yes, I'm getting answers. Very good. Ah, very good, very good. Weak base plus strong acid. And the strong acid should be in a small quantity. This should be the limiting reagent, right? Great. Okay. So which weak bases do you know? NH4OH. Strong acid, HCl. Okay, any other weak base? Yes. All the organic bases are weak base. Methylamine plus HCl. C6H5NH2. This is aniline plus HCl. Okay. And now what is it going to form? This will form NH4Cl plus water. CH3 NH3Cl C65H5NH3Cl. Here you have to put plus, here you have to put minus, plus and minus. Okay, or in a way you can also write, wait a second, you can also write by mixing weak base plus salt of its conjugate acid. Okay, fine. Or you can say that it which contains NH4, NH4Cl, which contains Na2CO3, NaHCO3, CH3NH2, CH3NH3 plus, Cl minus, C6H5NH2 and C6H5NH2, sorry, NH3 plus Cl minus. Okay. And in this case, the equation will be POH is equal to PKB plus log concentration of salt by concentration of base. Still me understood by everybody? And if you guys are copying, tell me whether you guys have copied it or not. Okay. Now let's go ahead and talk about the buffering action of a buffer solution. There's one hand raised over here. 1 second. Abhi, you raised a hand. Do you want to say something, Abhi? Or the things are clear? Do you want a mic, right, Abhi? No, Anshuman, the difference should not be of 1 OH, the difference should be of 1 H plus. Because over here, the conjugate acid will have 1 H plus extra. That is why. Abhi says S. I'm unable to understand. Abhi, please elaborate. Is it okay? Similarity at last also. I didn't got your point, Abhi. Okay, fine. Now see how the pH of the solution is the change in the pH of the solution is resisted. This is termed as buffering action. The buffering action is due to the buffer acidic and basic nature. See, when we are saying that we have got acetic acid, right, plus sodium acetate. So dear, this is having the buffer acidic part and this is having the buffer base part. Okay. So suppose you are adding HCl. So when you add HCl, what will happen? This salt will combine with HCl to form the solution. It is giving H plus in the form of the weak acid CH3COH. And if you look at the pH expression now, this will become pKa plus log S minus X upon A plus X. So if you see, there is a marginal change in the pH over here because of the addition of a small quantity. Please remember, this X is a small quantity. This cannot be big. Otherwise, the solution will no longer remain as a buffer solution. Like the example is the human blood, which is having a pH of 7 to 7.3. Okay. Understood? So if you add a huge amount of HCl into it, the person will die. The human will no longer exist in that case, right? Okay. Now you have added HCl over here. What if you add a base over here? This is A, this is X. This will be A minus X. This will be S plus X. So pH will be equal to how much? pKa plus log of. Okay. Fine. I hope you have understood this particular part. Shall we pick up some problems now? Tell me, dear friends. Shall I pick up some problems? Just one small thing over here I would like to tell you, that buffer capacity. Please note it down, all of you. This is equal to number of moles of acid or base added to 1 liter of solution upon change in pH. Okay, and phi will be maximum when now you would ask me, sir, how come? See, what is the expression of pH? pH is pK plus log salt by acid. If the concentration is same, this value will become equal to 1. Log of 1 is 0, so this becomes 0. So pH becomes equal to pK, which means, and pK is a constant. So pH becomes constant, which means there is no change in pH. When the change in pH is 0, buffer capacity will become infinite. Right? So they have asked this question in the exam. That's why I said, please note it down. Okay. Now let me give you some small questions. And then we will talk about the salt hydrolysis part. The question is, a weak acid has got Ka is equal to 10⁻⁴. So calculate the equilibrium constant for its reaction with strong base. This is a past year IIT problem. Similar buffering action is nothing but wherein on addition of a small amount of acid or a base, the pH is not changing much, and that is so because over here, let me show you. See over here, when you add a small amount of NaOH, what happens? The OH minus ion concentration doesn't go to the solution. It reacts with the buffer acid and forms this salt. So the change is reflected in the log part, which is very, very small. Okay, now solve this question, please. And it's a brainy question, so you need to apply your brain. Samaksh, you are saying no AV. Are you getting my audio and video clearly? No clues? I haven't got even a single answer till now. It is 10 raised to power minus 4. A weak acid has Ka is equal to 10 raised to power minus 4. Calculate the equilibrium constant for its reaction with strong base. Samaksh beta, I have explained over here. First of all, tell me, are you getting the AB or not? Are you getting the AB or not? Tell me. Now fine. See, over here I have said, let's see, this is a acid, this is the salt. If you add a base to this buffer, this OH minus ion doesn't go directly to the solution. It reacts with the buffer acid part, forms the buffer salt part, and thus you see this will be the new equation for pH. So the change in pH is resisted because the change occurs in this log part and doesn't directly add up to the solution. Okay. Now let us look at this particular part. See, when you are having a weak acid, let us say weak acid is HA. It is reacting with a strong base BOH and is forming AB plus water. Okay. Now what we do is we dissociate or we show the ionic part of the strong electrolyte. So this is HA plus B plus OH minus giving A minus, or rather and B plus. So you see B plus and B plus will get cancelled out and you are going to get HA plus OH minus giving A minus. So the equilibrium constant will be A minus, upon HA into OH minus. Okay. Now also Ka is equal to H plus into A minus by HA. So from here I can say Ka by H plus is equal to A minus by H. So if you put this over here, you will be getting Ka by H plus into 1 by OH minus. Now how much is this? This is 10 raised to power minus 14. I have told you many a times. So the answer comes out to be this. Tell me, is this question clear to you guys now? Okay, do you want another question of IIT? Tell me. Do you want another question of IIT? Okay. It says the pH of blood is maintained by mixture of H2CO3 and NaCl3. Okay. Now he is asking what volume of 5 molar NaHCO3 should be mixed with 10 ml of blood which is having 2 molar of H2CO3 such that pH of the solution is 7.4. We are given Ka for H2CO3, okay. I hope the question is clear. Yeah, you can take any strong base. Yeah, Anshuman, I'll take that out in the last, don't worry. No, it is given to be 7.4 beta. pH is given to be 7.4. Shall I solve this problem? No, it is not 16. It is. This is the answer. Tell me, beta, shall I solve it? Is it done by all you guys? Okay, let me solve it. See, dear friends, it is not about too much of critical thinking. You just need to decipher what is the question giving to you. See, we know it very well that pH is equal to okay, we know this part. Now pH is given to be how much? K is this much. When the K is this much, how do you find the pK? Right? Now see, 7.8 can be written as log of 8 and 8 can be written as 2 raised to power 3. So you can write this part as minus 3 of log 2 plus log of 10 raised to power minus 7. So this is log 2 is 0.3, so this becomes 0.9 plus minus of 7. So this is 6.1. Okay, 6.1. Now when I said salt concentration, now which salt we are talking? This is the salt. Now molarity is 5. So number of moles will be 5 multiplied by final volume V upon 10 plus V. See, we are going to add VML na? In 10 ml. So the final volume will be 10 plus this V. What is the acid quantity given to you? 2 molar. 2. How much is the volume? 10. Okay. This will get cancelled out. So all you have to do was find out this V. This V comes out to be. Now tell me, is this clear to you guys? Is this clear to you guys? Okay. Now let us go ahead and pick up. There is so much of a space at the bottom. No space. Have we consumed all? Okay, let's take a new board now. The Samaksh is noting this. Okay, you may note down, beta. How to solve the log part? See beta, initially though you will be taking the use of calculators, but anyways in the question if you see they will be always giving you the values of logs. Okay, now I'm taking a new page. Here I'm giving you some formulae for the salt hydrolysis. Most of the times they ask you question based on this formula only. Now those of you who have not watched my videos, I'm just repeating this particular part. Let's see how do you get a salt. Strong acid plus strong base will give you a neutral salt. This will give you an acidic salt. Weak acid plus strong base will give you a basic salt. Weak acid plus weak base can give you a neutral salt, an acidic salt, a basic salt. Okay. Now neutral salt we are not going to work on. Acidic salt. For example, this is the salt NH4Cl. Now, when you add this salt to water, you are going to get NH4OH plus HCl. As H plus ions are released in the solution, we can say this is an acidic salt. If I write this in the ionic form, this is what I'll get. So this is how I can write the equation. I hope this part is clear. So this is the H plus. Now when I do the derivation part, first thing, as you can see, that we are hydrolyzing the cation. So this is termed as cationic hydrolysis. On hydrolyzing it and working out on the expressions, I'll be getting H is equal to under root of KH by C. KH is equal to KW by KB. And pH is equal to 7 minus half log C plus pKb. Okay. Now these are the expressions which you need to remember. Yes, what is the doubt? NH4OH will not split because this is a weak base. Same way when you are talking about a basic salt, here you will be doing an anionic hydrolysis. Here H will be same, KH by C, KW by K, and pH is equal to 7 plus half log C plus pK. Okay. In the third case, H is equal to KH upon 1 plus root of KH. KH is equal to KW by KA into KB. And pH is equal to okay. So the salt will be neutral when pKa is equal to pKb. Okay, tell me, is there any doubt in this point? वाली जो ट्रामाडोल है ये मेरे को सूट करती है, ट्रामासिप के नाम से मैं लेता हूँ, तो वो है क्या आपके पास? तो ओपियोइड कोई है नहीं आपके पास? ट्रामाडोल का कोई सॉर्ट रखते ही नहीं, कहाँ मिल जाएगी वैसे? हेलो Okay. When will the salt be acidic? When pK is lesser than pKb. When will the salt be basic? When pKa is greater than pKb. This is the outcome of the salt hydrolysis part. In a nutshell, in one page, I have told you everything. If you remember this much, you'll be able to solve all the questions. Shall we start with the questions? H is the degree of hydrolysis beta. Another IIT problem. Calculate pH of 0.5 molar NaCN solution. pKb of Cn minus is 4.70. And here I'm giving you the value of log of 0.5 minus 0.3. Yeah. The formulae that I've written, this is for all three salt. But then there are conditions. When the salt will be acidic, when basic, and when neutral. Bhavil says 2.2. Sorry, sir, 4.8. Okay. Bhavil, if you see properly, this is NaCN. So this is formed by mixing NaOH plus HCl, which means a strong base and a weak acid, which means that this will be a basic salt. And if this is a basic salt, it basically means that the pH has to be greater than 7 beta. So your answer of 4.8 is wrong. Just 1 second. This is POH. This is PO. Yeah. No, this is pH only. This is pH. Sorry. Anushka has got the answer which is close, not the exact one. Samaksh, you are not even close. Anushka, you're close but not exact. Please look at the question carefully. Please look at the question carefully. Anshuman has got the right answer, 11.5. Yes, Anshuman. Now let me tell you how you have got it. See, first of all, you see this is HCN. They have given the pKb of CN minus N. So the first trick over here was that pKa plus pKb of a given acid or a base is 14. So pKa over here would come out as 14 minus pKb which is 14 minus 4.7, which is 9.3. Okay, so you got this. So now what all I have to do is I have to put the value over here. So pH is equal to 7 plus half. Log C I have already given you as minus 0.3 plus pKa is 9.3, which is nothing but 7 plus 4.5, which is 11.5. Now see beta, this is, tell me, is this a difficult question or you were stuck with the language? Tell me. Okay. Now I am giving you another problem from IIT. Okay. Now see what is the problem. I am writing the question as it is. Try to appreciate this one. The dissociation constant of a substituted benzoic acid Please remember, all the organic acids are weak acids. Okay. Yeah. Solve it fast. See, this is an objective type problem. I really don't think you should be taking this much amount of a time. Let me solve it. See, this is the answer, my dear friends. Yes, Anshuma, answer is 8. I've shared one problem on WhatsApp and I want all of you to solve this problem, okay? Mithun says, so weak acid under very low concentrations have same basic behavior. How come basic? A weak acid is a weak acid. How come it can show a basic behavior, beta? This is salt, sodium salt. Sodium salt means you are combining it with the NaOH. So this weak acid is reacted with NaOH, which is a strong base, to get a sodium salt. That is why we are using the formula for salt hydrolysis, beta. This is the formula for a basic salt, isn't it? Okay, and I have sent a question on the WhatsApp. Okay, I would want that all of you must solve that problem and send the answers to me on WhatsApp only. No, I don't want it right now, Samaksh. You must solve it at your ease, at your convenience. You can solve that question and send that answers to me. Okay? Not right now. Now, the next thing that we have to study over here is solubility product. Also referred as Ksp. See, this is used for sparingly soluble salts. For example, salts of silver, okay, these are sparingly soluble salts. Okay. Then CaCO3, BaCO3, all these are sparingly soluble. Now see, what do you mean by the term solubility? See, let me explain this. See, this is pure solvent. When you add some salt into it, it has got some amount of concentration which we call as ionic concentration. Agreed? Okay. Secondly, you keep on adding till the solution becomes saturated. So here, whatever is the concentration, that is termed as solubility. Concentration at saturation point. Okay. Now suppose you have got a salt AXB1. Now this salt will dissociate like this. Okay. K will be this. Okay. Now if I take this thing over here, K into concentration of AXBY. This is Ksp. Okay. Now see, very important point. See, this right hand side is termed as ionic product. And this is termed as solubility product constant. Now see, what is the point? The point is there are three cases. First case, when Ksp is greater than Ip, that is ionic product, we will say solution is unsaturated. Solution is unsaturated. Okay. Second case, Ksp is equal to Ip. Here we will say that the solution is saturated and ionic equilibrium is established. Third case, Ksp is lesser than ionic product. So precipitation occurs over here because the ionic product is more, so precipitation occurs. I will discuss about this thing in details, but in the next class, because now I have to take some doubts also. Okay. But before we go ahead, there is a relation between Ksp and solubility, and that relation is given as x raised to power x, y raised to power y, s raised to power x plus 1. Okay, so they'll be asking a lot of questions based on this. So I'll take it further from here only in the next session. And now I am taking the doubts. So please raise your doubts, whatever you are having. So writing C minus alpha is wrong. No, writing C minus alpha is not wrong. But see what happens. Suppose you have written C minus alpha. Suppose the value of C is 1. Okay. And alpha is varying from 0 to 1. Fantastic. No worries. But what if you write C minus 2 alpha? Where C is 1, alpha is 0.7. Here you will get stuck. So you can write this part, but to be on a safer side, you should write C minus C alpha. Okay. General formula. Ionic product is nothing but this is ionic product. Na? Product of ionic concentration is ionic product. That's it. See, there is no ionic product for H2SO4 beta. For H2SO4, it will be H plus concentration square into SO4 2 minus ion. That's how you'll be writing it out. Clear? No. H plus is equal to OH minus ion. That is true for a neutral solution. The concentrations may vary with temperature, but otherwise it is the same. And solubility product, beta, H2SO4 is not a sparingly soluble salt, Samaksh. Please see, this is applicable only for sparingly soluble salt, beta. Beta, monoacidic means that the base is capable of releasing one OH minus ion, which means it is capable of neutralizing one H plus. That is why you use the term monoacidic. Okay. So monoacidic means a base is capable of neutralizing an acid having one H plus. This is the point. Sir, can we say that, sir, what are applications of buffer solutions in our daily life? Bhavil, blood is a buffer solution, beta. I think that's the biggest application that you can find. Samas, I think you are unnecessarily getting confused between IP and SP. See, ionic product is ionic product. It is not for a given salt, but solubility product is basically for a sparingly soluble salt. Anshuman, see, HCl is an acid. When it releases the H plus, and this is the conjugate base. So basically, this compound has got this part as the acidic one, and this part as the basic one. Okay, so if this is a strong acid, the conjugate base will be weak. If you have got a weak acid, the conjugate base will be strong. Sir, I read its application in electroplating. Beta, see, try to understand what happens when you're using a solution which is having very low change in the pH. You can, you can use it in electroplating, no issues with that part, but it is not something which is so very generic. I mean, every time you don't use Buffer solutions for electroplating. It can be used as one of the things, right? Yes, next out. Sir, how to take anti-log in questions? Don't worry, Anshuman. That is, see, calculators are there, and it is primarily for understanding purpose. The IT will not grill you how to calculate anti-log, so don't worry about that part. See, buffer capacity is the capacity of an individual buffer. Okay. And when you talk about buffer index basically it is the see, I tell you this part. If I want to define it out, buffer index it is the ratio of, it is a differential ratio rather, I should say. Okay, of so I should say D of number of moles base added D of pH. When you say buffer capacity, it can be written as minimum amount of acid or base required okay. You can write it like this. Yeah, it will be specified to you, Samraksh. It will for sure be specified to you. Okay, so great. This is all from my side. I'll see you in the next class. The next class will be starting with We'll be doing a bit of doubts on and question on this, and we'll start with the general organic chemistry in the next class. Okay, God bless all of you. Bye-bye.